Section: Introduction. In this section, we discuss the common belief that using large batch sizes enhances the stability of training language models. As a result, advanced optimizers that excel in large batch scenarios have become standard. We often simulate even larger batch sizes than what our device memory allows by using a technique called gradient accumulation. In experiments with small batch sizes, we notice spikes in loss and significant instability. While it is typical to reduce the learning rate for smaller batches, we usually keep other hyperparameters, like the decay rates for the first and second moments in Atom, constant across different batch sizes. We demonstrate that by fixing the half-life of the second moment instead of keeping its decay rate constant, we can achieve stable training even with a batch size of 1. This approach allows us to benefit from the computational advantages and increased robustness of small batch sizes. We find that in this small batch context, the convergence speed is less affected by optimizer hyperparameters, and momentum becomes less critical. Conversely, large batch sizes necessitate larger learning rates to offset the fewer steps taken within a given compute budget, which requires sophisticated optimizers to predict updates effectively. Interestingly, we discover that even basic stochastic gradient descent, SGD, can perform well with very small batch sizes, contrary to previous findings. This stability without momentum can save memory since we do not need to store the optimizer's state. We also revisit Attafactor, a memory-efficient version of Atom, and find it to be a strong alternative for small batch training, allowing us to work with larger models in memory-limited environments. Our findings suggest that instead of relying on gradient accumulation or maximizing batch sizes to fit device memory, we should consider using smaller batch sizes that simplify procedures and enhance computational efficiency. We recommend adopting the smallest batch size that optimizes model throughput, a practice that holds true for both pre-training and fine-tuning language models. In convex optimization, it is common to use larger batch sizes as the loss approaches a minimum. We argue that when the gradient noise is minimal, small batch sizes can yield similar gradient estimates to larger ones while requiring fewer computations. As we near convergence, the ratio of gradient noise to gradient magnitude often decreases, suggesting a need for larger batch sizes. However, we hypothesize that language model training typically operates in a regime where small batch sizes are efficient. The structure of our paper includes a background section on language model training optimization, followed by results showing that small batch sizes can match the performance of larger ones across various optimizers. We also provide scaling heuristics for Atom's hyperparameters that improve performance in larger settings. Our practical recommendations emphasize using the smallest batch size for optimal throughput and highlight Attafactor's advantages in memory and performance. We conclude with a discussion of open questions in the field. Our code is available for reference. Section Summary. In this section, we review optimization algorithms for language model training, highlighting that using smaller batch sizes can lead to stable training and computational advantages when hyperparameters like the decay rates in Atom are appropriately scaled. We also discuss the benefits of simpler optimizers like vanilla SGD and Attafactor in the small batch regime, suggesting that practitioners should prefer the smallest batch size that maximizes model throughput instead of relying on gradient accumulation. Section: Related work. In this section, we explore the topic of batch size, which has been extensively examined in both theoretical and practical contexts. We look at how batch size affects the optimization process, interacts with various optimizers, and influences optimal learning rates and momentum settings. Previous studies have also discussed related concepts, such as the advantages of using stochastic gradient descent, SGD, its implicit biases, and the comparison between stochastic and full batch optimization. However, we note that training modern language models is different from traditional settings, as it is not convex and does not involve multiple epochs like in vision tasks. We often train with a limited number of tokens and stop before reaching convergence. This approach suggests that we could achieve better results by training larger models with fewer tokens. Therefore, some previous assumptions, like the need for larger batch sizes during convergence, may not hold true. We focus on research specifically related to modern language model training and examine the critical batch size, which is the point where increasing data parallelism yields diminishing returns. We find that any batch size below this critical point performs similarly when training for the same number of tokens. Contrary to earlier findings, we demonstrate that small batch sizes, even as small as 1, can perform just as well or better than larger sizes. Additionally, we show that small batches are more resilient to changes in optimizer and hyperparameter choices, allowing SGD to compete effectively. We validate our results on language models with modern architectures and up to 1.3 billion parameters. Some studies argue that the noise from gradients in small batches does not provide the same performance benefits in single epoch training as it does in multiple epoch scenarios. Other experiments suggest that small batches may not perform as well as large ones for models trained on specific datasets, but these studies often do not adjust the decay rates of the atom optimizer. We challenge these conclusions by reproducing their experiments and showing that their results stem from inadequate hyperparameter tuning. By properly adjusting the decay rates, we find that small batch sizes can be competitive. We also train language models on a dataset using various optimizers, including atom, lion, attefactor with momentum, SGD with momentum, and signed SGD with momentum. Our findings indicate that all optimizers, except for SGD, achieve similar performance and robustness to hyperparameters. In our experiments, we revisit the belief that larger batch sizes and advanced optimizers are essential for stable language model training. We argue that these beliefs arise from poor hyperparameter choices and specific experimental setups. We conduct a thorough grid search over hyperparameters and batch sizes for several optimizers. Due to the complexity of grid searches, we focus on a smaller model with 30 million parameters and use these results to develop heuristics for scaling hyperparameters across different batch sizes. We then validate our findings on larger models like GPT-2 and GPT-3. We train our 30 million parameter model on 600 million tokens from the Fine Web Hadoop dataset, following established scaling laws. Our model incorporates modern design features and we perform a detailed grid search over the hyperparameters of various optimizers. Our results show that all optimizers perform best at the smallest batch size, with performance declining as batch size increases, and the differences between optimizers becoming more pronounced. We hypothesize that larger batch sizes require more sophisticated optimizers because they involve making predictions about the loss function further from the current parameters. This makes the prediction problem more challenging, necessitating better-tuned optimizers. Additionally, we explain that momentum is less critical for small batch sizes because small steps do not overshoot the minimum, reducing the need for oscillation dampening. In summary, we find that SGD without momentum can perform competitively for small batch sizes. Section Summary. In this section, we challenge the prevailing belief that larger batch sizes and sophisticated optimizers are necessary for stable language model training, demonstrating that small batch sizes can perform equally well or better than larger ones when hyperparameters are properly tuned. Our experiments reveal that all tested optimizers, including SGD, achieve optimal performance at smaller batch sizes, suggesting that the need for complex optimizers diminishes in this regime. Section. Large batch training is sensitive to hyperparameters. In this section, we evaluate how sensitive large batch training is to hyperparameters. To do this, we analyze the optimal hyperparameters that minimize validation loss for the atom optimizer using a model with 30 million parameters trained on the Fine Web Hadoop dataset. We present the changes in loss compared to the lowest loss achieved across various batch sizes, from 1 to 4096. On the x-axis, we show the scaled values of hyperparameters relative to those that produce the best loss. This rescaling helps us compare results across different batch sizes, as their optimal hyperparameters differ. We find that smaller batch sizes are much more robust to changes in atoms' hyperparameters than larger ones. Notably, a batch size of 1 maintains nearly optimal loss across a wide range of learning rates and decay parameters, while larger batches see a sharp increase in loss with hyperparameter variations. To further illustrate this robustness, we conduct a two-dimensional analysis of both the learning rate and decay rate on a GPT-2 model. Consistent with our earlier findings, a batch size of 1 shows a much wider area of low loss compared to a batch size of 512. Therefore, when considering both the cost of a single training run and the budget for tuning hyperparameters, smaller batch sizes may be more advantageous. We also explore why smaller batch sizes are more forgiving with hyperparameter choices. We hypothesize that larger batch sizes need careful tuning because they require larger step sizes, which means they make predictions about the loss surface that are further from the current parameter values. Next, we apply our grid search results to test existing scaling laws for atom hyperparameters and develop new scaling guidelines. We analyze the validation loss for different atom hyperparameters, including the learning rate and decay parameters. Our findings reveal that the commonly used square root scaling for the learning rate does not hold. Instead, we find that it scales more slowly than expected. For example, when increasing the batch size from 1 to 1024, the learning rate should only be scaled by about 3 times, rather than the 32 times suggested by the square root rule. We confirm that the default value of the first moment decay works well across batch sizes, but keeping the second moment decay fixed does not scale effectively for smaller batches, which need a larger value. However, maintaining the second moment decay's half-life at its optimal value as we adjust batch sizes provides good performance without needing to retune this hyperparameter. We then test our scaling guidelines in a different context, where a decoder-only transformer is trained with Atom on the C4 dataset. We reproduce previous results showing that smaller batch sizes perform worse than larger ones when only the learning rate is tuned. By applying our scaling recommendation for the second moment decay, we achieve much better results, with smaller batch sizes performing comparably to larger ones. This suggests that earlier findings may have stemmed from inadequate hyperparameter tuning and that our simple scaling approach is applicable in other scenarios. Section Summary. In this section, we evaluate the sensitivity of large batch training to hyperparameters and find that smaller batch sizes are more robust, achieving nearly optimal loss across a wider range of hyperparameter values. We also propose scaling heuristics for Atom's hyperparameters, demonstrating that with proper adjustments, smaller batch sizes can perform comparably to larger ones without extensive tuning. Section. SGD performs competitively with adaptive optimizers at the billion-plus parameter scale. In this section, we present our findings on how stochastic gradient descent, SGD, competes well with adaptive optimizers when dealing with models that have over a billion parameters. From our experiments with models containing 30 million parameters, we conclude that 1. Smaller batch sizes can perform just as well, or even better, than larger ones. 2. Smaller batch sizes need simpler optimizers and are less sensitive to incorrect hyperparameters. 3. Specifically, basic SGD can hold its own against adaptive optimizers when using small batch sizes. And 4. We introduce a new method for adjusting a specific parameter to maintain a consistent half-life, which we find improves performance. To test these insights on a larger scale, we trained GPT-2, 124 million parameters, and GPT-3, 1.3 billion parameters, using the Fine Web dataset. For the larger model, tuning the learning rate for each optimizer was too resource-intensive, so we used Atom W with default settings as our baseline. When using a batch size of 1 with Atom, we did not adjust any hyperparameters, turning off weight decay and scaling the learning rate based on our earlier findings. We compared two methods for adjusting the specific parameter, keeping it constant versus fixing the half-life. We also tested 4 learning rates for Attafactor and SGD since we lacked reference values for these optimizers. Interestingly, we found that SGD matched the performance of the Atom W baseline, while both Atom and Attafactor with a batch size of 1 outperformed it. For the smaller model, we followed the same approach but tuned the learning rate for each optimizer, which enhanced the Atom W baseline's performance. In our exploration of fine-tuning, we confirmed that our results apply even when training for multiple epochs. Given that memory can be a limiting factor when fine-tuning large models, it is common to freeze model weights and only train low-rank adaptation (LoRa) modules, which reduces the number of parameters that need training and thus the memory required. We observed that Adafactor with a batch size of 1 performed similarly to Atom while maintaining a comparable memory footprint to LoRa. Additionally, Atom with a batch size of 1 and our hyperparameter scaling performed at least as well as Atom with a batch size of 16 during fine-tuning. However, LoRa performed significantly worse than full-parameter fine-tuning, as noted in previous studies. Therefore, we suggest that in memory-limited situations, full fine-tuning with a small batch size is likely a better option than using LoRa, as it avoids the need to store accumulated gradients and allows for the use of memory-efficient optimizers like Adafactor without sacrificing performance. Regarding practical recommendations, we note that training large language models typically requires substantial GPU resources and large batch sizes, which also necessitate advanced optimizers. However, when pre-training or fine-tuning on a single device, memory can quickly become a constraint. We need to keep the model, optimizer state, forward pass activations, and possibly accumulated gradients in memory. Using the larger GPT-3 model as an example, we illustrate that storing all values in a specific precision and checkpointing gradients after each transformer block can make using large batch sizes with Atom impractical on consumer-level GPUs. In contrast, training with SGD, which does not maintain state, or Adafactor, which has minimal state requirements, is entirely feasible on such GPUs. Importantly, as we have shown, these simpler optimizers achieve the best performance with small batch sizes, often matching or exceeding the performance of more complex optimizers that use larger batch sizes. Section Summary. In this section, we demonstrate that small batch sizes can match or exceed the performance of larger ones, and that simple optimizers like vanilla SGD and Adafactor are effective and memory-efficient alternatives to more complex optimizers, especially in fine-tuning scenarios. We recommend full fine-tuning with small batch sizes over low-rank adaptation, LoRa, to optimize performance while managing memory constraints. Section: Hardware Utilization. In this section, we recommend setting the batch size to the smallest amount that maximizes how quickly the model processes data, measured in tokens per second or model flops utilization. To do this, we need to avoid limitations from memory bandwidth, which typically means using a batch size of several hundred tokens per device. We also note that second-order optimizers, like Muon, add a fixed computational cost for each optimization step. If the batch size is too small, this cost can lower the model's processing speed. If we encounter any of these limitations, we suggest increasing the batch size. We demonstrate that small batch sizes, even as low as 1, can consistently match or exceed the performance of larger batches when properly tuned, both during pre-training and fine-tuning. Specifically, using stochastic gradient descent with a batch size of 1 performs similarly to the Atom W baseline for GPT-3 with minimal adjustments. We also introduce a straightforward scaling rule for a specific parameter based on a fixed second moment half-life in tokens, which applies across different model sizes. Our findings challenge the common belief that larger batch training is always better and suggest avoiding gradient accumulation while using simpler optimizers when memory is limited. Several questions remain. How do our findings relate to batch size schedules? Can we create more effective optimizers with smaller memory requirements tailored for small batch sizes? And can we understand theoretically why fixing the second moment half-life in tokens works across different scales?